Okay, listen to this. Digital slide rulers over circular helical tape. Just let that phrase sink in for a second. It honestly sounds like something straight out of a retrofuturistic sci-fi novel, doesn't it? But we're actually not talking about science fiction today. We are looking at a very real, incredibly profound way of completely reimagining how computers read, process, and navigate data. Welcome to The Explainer. Today, we're diving deep into the OMI-ISA project. It is a fascinating, almost brutalist approach to computer architecture. We are exploring an extreme low-level system where classic retro computing philosophies just absolutely collide with radical minimalism. It's an environment where all those comfortable safety nets of modern programming, they're completely stripped away. And it forces us to think about code not just as text on a screen, but as physical, structured space. So, here is exactly what we're getting into today. We'll start with the slide rule inspiration, then look at carriers versus languages, check out the SP boundary fix, dive into the minimalist instruction set, tackle the hex parsing problem, and finally wrap up with the lookup table solution. All right, part one, the slide rule inspiration. To really grasp the architecture of OMI, we actually have to look backward at how we used to physically interact with data. Modern programming languages generally assume that source code is just this endless, linear stream of text. But look at how things used to be built. Early storage wasn't just raw text, it was structured inside physical containers. Think about a punch card. It had a physical header and distinct columns. Magnetic tape used a leader, sync markers, and trailers to physically frame the records. And honestly, network packets still work exactly this way today, using preambles and payloads. Well, the OMI project revives this paradigm. It introduces something called a carrier, meaning before you even get to the executable payload, there is a physical style container wrapped around it, complete with gauge markers and control codes. It's literally a media model inspired directly by the robust framing of older physical storage systems. And because of that container model, memory navigation inside the OMI system is entirely reimagined. A normal compiler just thinks of memory addresses as a straight linear sequence of bytes, right? Byte 1, byte 2, byte 3. But in OMI, navigation works a lot more like aligning the scales on a circular slide rule. Addresses act as structured coordinates in a hierarchical space. So the question isn't just where is this byte, but rather where does this node live within the overall hierarchy of the transport envelope? That is absolutely crucial to understand. OMI isn't just a language, it's a deeply structured navigation model. Which brings us right to section 2, carriers versus languages. This was arguably the biggest aha moment in the entire project's development. If we have a container and we have a language, those two things cannot bleed into each other. Enter the gauge preheader. In the OMI-ISA project, the developers designed a strict 8-byte sequence, what they call a binary shebang, that acts as the transport envelope. It identifies the format, establishes hierarchical separators, and opens up the readable surface. It is the box that holds the data. And the critical point here is that this header exists entirely outside the syntax of the programming language itself. It is purely a transport mechanism. And this brilliantly illustrates the separation of responsibilities. You've got layer 0, the carrier layer. Its absolute only job is to deal with that binary shebang, check the formatting, and then completely strip that transport data away. Then, and only then, do we hand the pristine payload over to layer 1, the parser. The parser begins its job at absolute byte 0 of the payload. It has literally no idea that the framing bytes ever even existed. The container and the contents are perfectly isolated. Let's move to section 3, the SP boundary fix, because, well, theory is great, but implementation is where it always gets messy. Early on in the coding phase, they had a bit of a hack in the system. The parser itself was responsible for skipping over the last byte of the preheader, which was a space character, or SP, just to get to the code. So it was conflating the carrier layer and the language layer. And as we just talked about, that breaks the whole philosophy. So the developers completely restructured the C code. They created a dedicated loader file that cleanly strips the preheader first. This meant they could fix the parse function so it strictly starts at payload byte 0. The loader handles the envelope, the parser handles the logic, and the whole architecture remains wonderfully clean. Okay, section 4, the minimalist instruction set. With the architecture cleaned up, the project moved toward writing a self-hosting compiler. And man, this is where the environment becomes absolutely punishing. The OMI instruction set is brutally minimalist. Imagine trying to write complex parsing software, but I tell you that you have no bitwise and or operations. You want to mask out a specific bit? Yeah, you can't. Even worse, there is no conditional branching based on standard comparisons. You literally cannot ask the CPU, hey, if register A is greater than register B, jump here. No way. The only control flow instruction you have at your disposal is JZ, jump if 0. That's the whole shebang. If a register is exactly 0, it jumps. If it's any other number, it doesn't. You are forced to rely entirely on basic addition, subtraction, and XOR to do everything. It is an unbelievably restrictive box to work in. And that extreme restriction leads us to the climax of the project's coding narrative, Section 5, the hex parsing problem. I want you to really think about this puzzle for a second. How do you check if a character you just read from a text file is a valid hexadecimal digit, meaning it's 0 through 9, lowercase a through f, or uppercase a through f, when you have no basic comparison instructions and no bounds checking? In a normal system, you just write, if character is greater than or equal to a and less than or equal to f, but we have no and we have no less than. So what do? The developer logs show this agonizing series of increasingly convoluted attempts to solve this. First, they tried subtracting the minimum range value from the character itself. Okay, so take the character and subtract the value of 0. But then what? You still have to see if the result is between 0 and 9. They tried exploiting unsigned integer wrapping, basically hoping to see if the math rolled backward past 0, sort of like a car odometer rolling back. But remember, the only tool they have is JZ. And JZ can only check for absolute 0. It can't check if a number is negative or if a high bit is set. Nothing. It just became this tangled, virtually impossible web of manual subtraction and failed branching. Under these minimalist constraints, standard character classification was fundamentally broken. But you know what they say, constraints breed creativity. Section 6, the lookup table solution. When you can't compute your way out of a problem, you find a workaround. And the solution they finally landed on is beautifully simple. Instead of trying to use arithmetic to validate a character, they just built a map. They created a 256-byte hex lookup table directly in memory. For every single possible byte value, from 0 to 255, the table stores a specific answer. If the byte represents the character 0, the table holds a 0. If it represents A, it holds a 10. If it represents a random character like Z, it holds an invalid marker, like 0fx. By pre-computing these values into memory, all that complex, impossible branching logic is completely replaced by a single elegant memory load command. You just look up the character's index, and boom, the table gives you the exact answer instantly. And what makes this truly brilliant is where this table is built. Writing 256 entries inside that restrictive virtual machine would take hundreds of painful instructions. So instead, they shifted the burden. The C host, the layer that initializes the entire environment, preloads this table into memory before the minimal virtual machine even boots up. By the time the self-hosting compiler actually starts running, the map is already there waiting for it. The code remains remarkably clean, it's fast, and it completely bypasses the limitations of the CPU. It's honestly an incredible journey, from high-level philosophies of physical data framing all the way down to the exact byte-level tricks required to make it actually work. The OMI-ISA project proves that radical minimalism isn't just some fun aesthetic. It fundamentally changes how we approach and solve computing problems. It really makes you wonder, what other modern, heavily bloated systems could be radically simplified and improved if we just return to the structured, minimal logic of punch cards and slide rules? Thanks so much for joining me on this explainer, and keep questioning the architecture beneath your code.